Hello guys, and welcome once more to this new video into our YouTube channel. So in today's video we are going to be solving a question on mechanics. More specifically, we are going to be solving a question on center of mass. So in today's video we are going to be solving a Cameroon GC examination, pure mathematics mechanics, paper 3 of June 2024. So we are going to be solving question 7 Romans 1. So this question came on center of mass. The question reads: a trapezium ABCD with uniform density is such that AB equals 4 meters and BC equals CD equals DA equals 2 meters. In the A part, we are asked to show that the center of mass of the lamina is 4 square root of 3 divided by 9 meters from AB. Next question is being introduced with a paragraph, that is, we are being told that the lamina is fully suspended from D and hangs in equilibrium. In the B part, we are asked to find the angle between DC and the vertical through T. Let's then actually launch into the solution of this question. So in the A part of the question, we are asked to show that the center of mass of the lamina is 4 square root of 3 divided by 9 meters from AB. Now, in the question we have a trapezium which is such that AB equals 4 meters, BC equals CD equals DA equals 2 meters. Now, from this data given to us, we can clearly conclude that the trapezium we are going to be working with in this particular question is an isosceles trapezium. Why? Because we have 3 sides of the trapezium which are equal in length, which actually equals 2 meters. And we have one side which is longer than the 3 other sides, that is 4 meters. From which we can therefore come forward with the diagram of our isosceles trapezium equation, where AB equals 4 meters, AD equals DC equals CD equals 2 meters. Now, in the question, we'll be asked to show that the center of mass of the lamina is given by this. Now, the best thing we can do is actually to split the isosceles trapezium into known portions. That is, we are going to split the trapezium into 2 triangles and 1 rectangle. Why are we doing this? We are doing this because for these portions, that is for the triangles, we clearly know that is the distance of the center of mass of these triangles from AB can be calculated in one condition that we know this height h, which we are going to determine in the calculations. Also, we know the distance of the center of mass of this rectangle from AB. Okay, now knowing this condition, we can therefore easily obtain the center of mass of the lamina. Why? Because the lamina is actually a composition of these three portions so far. Now, as I said, for us to launch forward with the calculation, we must first of all determine this height here, this distance here, h, which corresponds actually to the width of the rectangle and the height of the 2 triangles. Okay, which we are going to determine in this exercise, in this question. We are going to determine the distance h, because without the distance h, we cannot calculate the distance of the center of mass of these 2 triangles from AB as well. We can't calculate the distance of the center of mass of this rectangle from AB. So we need to determine this distance h. Okay. Also, we know that AB equals 4 meters, DC equals 2 meters. It means we can obtain the base of these 2 triangles so far. That the base of these 2 triangles is actually going to be 1 meter for the first one, the first triangle, and 1 meter for the second triangle. Why? Because if we do 1 plus 1, then plus 2, we get the distance AB, which is actually 4 meters. So the base of these 2 triangles being known, we are therefore going to obtain the height, the distance h, which corresponds to the height of the 2 triangles and as well the width of this rectangle. So from Pythagorean theorem, we can determine this h, that is h is actually equals to what? Since we know this distance AD equals 2 meters, and we also know the distance CD, obviously we can calculate the distance h. H here is going to be equals to 2 squared, which is the hypotenuse squared, then minus 1 squared, we actually give us square root of 3 as the distance of h. Okay, now having all these distances, that is having the distance h, having the base of these triangles, and obviously we know the length of this rectangle so far. So it means we can therefore calculate the different distances of the center of mass of each of the portions from AB. But before doing that, we are going to let gamma be the weight per unit area of the lamina. In this question, lamina we are working with is going to be a trapezium. Now, since we are solving the equation of center of mass, the best thing we can do is actually to come out with this table, which is constituted of the portion, the area, the width, the distance from AB, and the distance from the y-axis. Now, I added this distance from the y-axis because it's not being asked in the question. I added it just for us to exercise ourselves in getting distances of center of mass from a certain distance, that is from a certain point. Now, this portion is going to be constituted of the 2 triangles, our rectangle, and since the trapezium is the lamina which we want to determine its center of mass, it's actually a composition of these 3 portions. Now we are going to determine the area of each of the portions, their corresponding weight, their distances from AB, and the distances from the y-axis. Now, why are we doing this? Why are we coming out with this table? This table properly help us, or this table guides us to easily use the data, that is without making any mistake. So this table is very interesting. Why? Because from this table you can easily see that you can easily get the calculations without doing any mistakes so far. Because if you have the weight or the distance from AB of each of the portions, we can obviously get the weight of the trapezium by simply summing up the weight of these individual portions. Okay, and when you are going to be taking moment, you are going to clearly see what multiplies what. That is the corresponding force of the distance. That is the sum of the moment of the portion. That is the sum of the moment of the triangle, of the rectangle, and of this second order triangle is actually going to be equal to the moment of this laminar equation, which is actually the trapezium equation. So coming out with this table properly help you to easily see what multiplies what when you are going to take moment about the distance AB. Let's talk about determining the area of the triangle T1. The area of the triangle T1 is actually what? Half base times height. Half base here is 1, then the height here is what we have determined, which is actually square root of 3. Or which you can determine its width, which is actually the area times lambda, which we have let being the width per unit area of the lamina. We can also obtain the distance from AB of this triangle T1. That is, this triangle T1, the distance from AB is actually 1/3 of this height h. That is 1/3 of square root of 3. And obviously, the distance from the y-axis is actually what equals what? The distance from the y-axis, it is actually, the distance from the y-axis is actually 2/3 of this distance 1. That is 2/3 of this distance 1, which is actually 2/3, because 2/3 times 1 still give us 2/3 so far. Okay, yes. Now, similarly for the rectangle, the area of the rectangle is actually length times width. The length is actually 2, the width is actually 8, which we have determined to be square root of 3. The reason why the area of this rectangle is 2 times square root of 3. Then the weight is simply 2 times square root of 3 times lambda. Then the distance from AB is actually going to be equal to square root of 3 divided by 2. Why? Because knowing this h, the distance from AB of this rectangle is actually half of this distance, which is half of square root of 3, which is actually square root of 3 divided by 2. And also the distance from the y-axis, that the distance from the y-axis is going to be half the distance DC, which is actually 2 meters. So half of 2 meters is actually 1. Then plus this other one give us 2 to be the distance from the y-axis of our rectangle equation. So also for the second triangle, the area of the second triangle is actually half base times height. Half base here is 1, the height is square root of 3, which we have determined. Obviously its weight is actually going to be square root of 3 divided by 2 times gamma. And the distance from AB of this second triangle is actually half, is actually 1/3, which means it's 1/3 of this height h, which we have determined. That is 1/3 of square root of 3. And the distance from the y-axis of this second triangle is what? Now, since we want the distance from the y-axis of the second triangle, we are first of all going to consider this distance here. That is 1 meter plus 2 meters, because we know that this is actually 2 meters. So 1 meter plus 2 meters will give us 3 meters. Then this small distance, that is about the center of mass of the second triangle, that is, it is 1/3. It is actually 1/3 of this distance here. Because if you try to incline this triangle to look like this one, that is to look upright like this one, you can clearly see that the distance actually, okay, of the center of mass of this triangle T2 from this point, see, is actually 1/3 of this distance 1 meter. So we are going to have 1/3 of this 1 meter, which is actually 1/3, then plus 3, that is plus the 2 plus 1, which we have obtained. So 1 plus 2 will give us 3, then 3 plus 1/3 of this 1 meter will give actually 10 divided by 3. Now, since we already know the area of each of the portions, we can clearly conclude that the sum of this area give us the sum of the unit which we want to determine its center of mass. That is the sum of these 3 portions. Give us the sum of the area of these 3 portions. Give us the area of the trapezium. Its corresponding with actually 3 square root of 3 times lambda. Then the distance from AB is actually what we are determined is actually y bar. That is the distance of this trapezium from AB. From AB is actually y bar so far. Okay, yes. And obviously the distance from the y-axis is actually x bar. But in this particular question, we are going to look it for. That's we are going to find this x bar. Okay, just for us to exercise ourselves in getting the distances of the different trapezium as well from the y-axis. Okay. Now, since we want only the y bar, that's the distance from AB of the lamina, we are simply going to take moment about AB. Now, taking moment about AB, we are going to have what? The sum. We are going to have the sum of the moment of the individual portion to be equal to the moment of the uniform, that is because the moment of this lamina about AB. Now doing that, in that we are going to have what? The weight of triangle 1 times the distance from AB, okay, plus the weight of the rectangle times the distance from AB, this, then plus the weight of the triangle T2, okay, which is this, then times the distance from A, which is this, okay, to be equals to the moment of the lamina, that is this. That's the lamina, which is actually the sum of the individual portions, and its moment about AB is actually what? It's actually its weight, okay, which is actually the sum of the weight of the individual portions, then times y bar, which we want to determine, okay. For which, further simplifying, we are going to have a half of lambda, then plus 3 lambda plus a half lambda to be equal to 3 square root of 3 lambda, okay. Yes, from which, further simplifying again, we are going to obtain 4 lambda. Why? Because a half lambda plus a half lambda give us 1 lambda. We give us 1 lambda, which is actually lambda. The lambda plus 3 lambda give us 4 lambda to be equal to 3 square root of 3 y bar, from which we can therefore conclude that y bar, which is the distance from AB of the lamina, okay, from AB, obviously is actually equal to 4 square root of 4 divided by 3 square root of 3 meters. When you multiply top and bottom with the square root of 3, we are going to have y bar, which is the distance from AB of the lamina, to be equal to 4 times square root of 3 divided by 9 meters, which was actually what was required for us to prove in the A part of the question. Okay, the B part of the question asks us to find the angle between DC and the vertical through D. Let us go back and illustrate our trapezium which we had, where AB was given to be 4 meters, AD equals DC equals CB equals 2 meters. Let us indicate the center of mass of our trapezium, and since they're asking us to find the angle between DC and the vertical through D, that angle is going to correspond to this. Take note, it's very, very important. So since they're asking us to get the angle between DC and the vertical through D, we must first of all indicate that angle in the trapezium, and that angle corresponds to this angle theta. So this angle theta corresponds to the angle between DC and the vertical through D. Okay, yes, knowing that obviously AB equals 4 meters, BC equals CD equals ZB equals 2 meters. Let this point be N. Why are we putting this N? Because for us to get this angle theta, the best thing we can do is actually to first of all find tan theta. Okay, that is tan theta here is going to be opposite side, which is NG, divided by adjacent side, which actually ND, which we are going to determine in this question. So we are going to determine NG and ND, and knowing that, we are therefore going to apply the fact that tan theta equals opposite side, that is NG, okay, divided by adjacent side, which is actually ND. Okay, yes. So in the place from the figure, as I said, tan theta equals opposite side, which is NG, divided by adjacent side, which is actually ND. So we're going to determine this NG and ND and get tan theta. After tan theta being obtained, we are going to therefore find the angle theta being asked for us to determine in the B part of the question. So obviously, knowing that NG is actually equals to what? NG here is actually equal to this whole distance, that is square root of 3, which we have obtained, which was h, which we have obtained to be square root of 3, which we obtained by using Pythagoras theorem. Then minus y bar. Remember, the distance from G to this point, that the distance of the center of mass of this lamina from AB is actually y bar, which we have determined in the A part of the question. So the distance NG is going to correspond to the whole distance square root of 3, then minus y bar, which we have determined in the A part of the question. So it implies NG is going to be equal to square root of 3 minus 4 square root of 3 divided by 9, which will actually 5 square root of 3 divided by 9 as the distance NG. Let us move forward and then obtain ND. ND here is actually going to be equal to what? X bar minus 1. Why x bar minus 1? Remember, this x bar is actually the distance from the y-axis. This x bar is actually the distance from the y-axis of this lamina, which I told you guys that we should put in the table, for it's going to help us furthermore in this exercise, in this question. Okay, or that this is it helping us. So this x bar, we are going to determine this x bar. We can easily determine this x bar. That is, since the isosceles trapezium is symmetric about its center of gravity, it means this x bar is going to be equal to what? 1 plus this 1. Okay, which actually corresponds to the distance of the center of mass of the lamina from the y-axis. Very important. Okay, we are doing this because the isosceles trapezium is symmetric about its center of gravity. If it was not the case, we would not have done this, that we would not have added 1 plus 1 to get this x bar to be actually equal to 2. But remember, as I said, we can still prove this. Okay, that's it. It can also be proven that x bar equals 2 by taking moment about the y-axis from the table we constructed in the A part of the equation. So let us do that and see whether we are going to obtain the same 2 which we had by considering the fact that the isosceles trapezium was symmetric about its center of gravity. Let us prove that. So if we take moment about the y-axis, obviously from the table we had, taking moment about the y-axis, we are going to have what? We are going to have the corresponding weights of the portions. That is, taking moment about the y-axis, we are going to do is going to be the sum of the moments of the portions, okay, about the y-axis to be equal to the moment of the trapezium, which is actually the lamina, from the y-axis. So doing that, we are going to obtain this. That is where this one 2/3 correspond to what? 2/3 correspond to where 2/3 here correspond to the distance from the y-axis of the triangle T1, then times its weight, then plus 2, which corresponds to the distance from the y-axis of the rectangle, okay, then times its weight, which actually 2 square root of 3 times lambda, then plus 10 divided by 3, which corresponds to the distance from the y-axis of the second triangle, okay, then times its weight, which actually square root of 3 divided by 2, then lambda, to be equals to the weight of the whole lamina, which is actually 3 square root of 3 lambda, then times x bar here corresponding effectively to distance from the y-axis of the lamina, okay, which we want to obtain here. So from which, further simplifying, we are going to obtain square root of 3 divided by 3 lambda, then plus 4 times square root of 3 lambda plus 5 square root of 3 divided by 3 lambda to be equal to 3 square root of 3 times x bar. Further simplifying, we are going to obtain obviously x bar to be equal to 2. That is, from here we can clearly see that we can multiply. From here we can easily obtain that. That is, if we simplify it, that is, here we have square root of 3, that is square root of 3 divided by 3 lambda, then plus 5 square root of 3 divided by 3 lambda, from which summing up the 2, we are going to get 6. We are going to get 6 square root of 3, okay, divided by 3, then plus 4 square root of 3 lambda, then plus 4 square root of 3 lambda, okay, from which, further simplifying, we are going to get what? We are going to obtain 6 square root of 3 lambda, the left hand side, to be equal to 3 square root of 3 times x bar, which therefore implies that what? X bar here is going to give us 2, simply because if we divide both sides of the equations with 3 square root of 3, we are easily going to obtain the x bar to be actually equal to 2. And which was actually what we obtained when we consider the fact that the isosceles trapezium was symmetric about its center of gravity, okay, which is actually a good thing, a very good conclusion, very important. Now from which is actually what we have obtained previously. So knowing already the x bar, it means we already know nd, and knowing ng, we can therefore obtain tan theta, and knowing tan theta, we can therefore obtain theta, which corresponds to the angle between DC and the vertical through D. So obtaining therefore, that is knowing nd to be equal to x bar minus 1, that is 2 minus 1 give us 1. Obviously we can therefore obtain tan theta, which is actually ng, which is what we obtain to be 5 square root of 2 divided by 9, okay, then ng, then divided by nd is actually 1, from which tan theta is going to be equal to 5 square root of 3 divided by 9, and from which we can therefore obtain the value of theta, which corresponds to the angle between DC and the vertical through D, which theta here is simply going to be tan inverse of this value, which gives us 43.90 degrees as the angle between DC and the vertical through D, and which was actually what required for us to determine in the B part of the equation. So thank you very much for watching this video, and don't forget to like, subscribe, share for the others to benefit from the content. So thank you very much, and remain tuned for a very next interesting video. Bye bye.